Alright, so this problem says select 3 different US coins. We want to measure the diameter of each coin separately and give units and uncertainty. We also want to give the right number of significant figures for each diameter. We're going to place all the 3 coins in a row along a straight horizontal line with their diameters touching each other. And we want to calculate the total distance d1 plus d2 plus d3 across those coins using the conventions of adding with significant figures. And this will be the total distance from the left side of the first coin to the right side of the final coin. Alright, I got 3 coins here. Alright, so this distance here can be called d1. This can be d2 and d3. I'm going to just measure the coin just straight across. My ruler was marked to the 10th of a centimeter. Okay, so let me go ahead and measure my $half. It looks like it's maybe 3.0 centimeters. So I'm gonna put 3.00 centimeters for D1. Alright, now why did I use that number of zeros? Because my ruler is marked to the 10th of a centimeter, so I'm supposed to estimate 1 digit beyond the 10th, so I should definitely give 100th. But if you put it in millimeters, my ruler is marked to the millimeter, right? So I have to go 1 digit beyond that, so I should put 30.0 millimeters. These both represent the same measurement, and they have the same number of significant figures. They're called, 3 significant figures, right? Now, the thing is that you can't actually stop there when it comes to measurement. We actually have to give what's called an uncertainty. This here is the best estimate, it's called. And then we have to say plus or minus some amount of uncertainty. So, with that in mind, what should we put here? Well, it's a common rule of thumb to let the uncertainty be half of the smallest marking on the instrument. So if your instrument's marked to the 10th, you should say that the uncertainty could be as small as 5/100ths. Now you want your final digit of your uncertainty to be in the same place value as the final digit in your best estimate. Like, that's a principle to try to always follow whenever possible. Okay. Well, we just want to go, forward and do that with all the different coins. So I said that this one was going to be a $half. This one is a quarter. And this one can be a penny. Alright, so I'm just going to measure my quarter now. 2.37 perhaps centimeters. I say 2.37. And then of course we have to put plus or minus the uncertainty, which it would be reasonable to have the same uncertainty here. Some people will use just 1/100th, a tenth of the smallest marking on the ruler. I'm not feeling like I'm that accurate with my, it's a little dark in here, so I'm thinking 5/10 of the smallest marking is probably reasonable here. All right, and then I'll do the penny. Okay. I say 1.88 centimeters. All right, great. So our next task is to see if we can calculate what is the distance across all the coins if they're lined up like this. Okay, this would be D1 plus D2 plus D3 to do that. So for this, what I usually do is just add them up according to the old school grade school way, actually. You got to line up their place values. All right, now this one, it's kind of an easy one because they all had the same precision, and you have to decide how many significant figures to keep. In this case, it's easy to tell how many to keep. You got to keep them all. So because all of my measurements were given to the hundredth, okay, like I want to keep a 100th digit in my final answer as well. Okay, so 7.25 is a good final result here. Okay, but now the hard part. We have to figure out how much uncertainty there is in the result of the calculation. That's tougher to do. Now, one of the most basic ways of finding out how much uncertainty there could be would be to just add the uncertainties. So you could say if the one coin could be as much as 0.05 off, and the second coin could be 0.05 off as well, and the third coin could be 0.05 off, then perhaps the final result could be up to 0.15 off. That's one option. The idea is that you have a best estimate and an uncertainty in that estimate as well. Okay, then we have B plus or minus sigma B. And then here we have C plus or minus sigma C. Now what we're doing is we're finding the result of a calculation. I'm going to call it R, which is standing for the result of the calculation. And it's found by adding A plus B plus C. And so there's this formula for the uncertainty in R as well. We already know what the uncertainty in A is, and we know what the uncertainty in B is, and we know the uncertainty in C because we gave them, right here. So we know those. But what we don't know is the uncertainty in R, and that's what we're trying to find. So there's a formula for it, and it's kind of a complicated formula. What it says is the formula will be the square root of a partial derivative of R with respect to one of the variables involved times the uncertainty in that variable, and then we have to square that. And you do that for as many different variables as you have in the calculation. Now I'll explain what these symbols mean here. So the little symbol here that looks like a 2, it's a partial derivative operator. So like you can have like dr over dA. Okay, and that would be the that would be the derivative of r with respect to the variable a. All right, so a partial derivative is a little different. All right, so we have this different notation. And what it means is the partial derivative of r with respect to a. All right, so what's the difference? First of all, let's find the derivative of r with respect to a, and then we'll compare it to the partial derivative. So you got r equals a plus b plus c. You leave it in variable form. You don't plug in the numbers just yet. You have 3 variables, right? So if you wanted to find dr over dA, then you would just do this, d over dA of all this stuff. But right now, we don't assume that any of these are constant. We just assume that they could be functions of a. Okay, and if they're functions of a, then at least this one's easy to do. dA over dA. That's easy. But here you'd have dB over dA, and then dC over dA. Okay, dA over dA is just 1. So 1 plus dB over dA plus dC over dA, and that'd be as far as I can go, since I don't have any other expression for B and C. When you're doing a partial derivative, you don't worry about dB over dA and dC over dA, because you treat all variables except for a as if they were numbers, as if they were constants. So that's the difference between like derivative and partial derivative. So now let's do it. Let's treat them as if they were constants. So you got r equals a plus b plus c. We now want to find the partial derivative of r with respect to a. So you do this. But this thing, b, would be treated as if it was a number. And the derivative of a number would be 0. And so what you end up having is that the partial derivative with respect to a is simply 1, and you don't worry about those other terms that we had in the other case. You could almost imagine it like as if it was like r equals a plus 2 plus 3. And you want to find the derivative of that with respect to a, right? So you got a plus 2 plus 3, and take the derivative of it, right? The variable, you just attach its constant, like its constant would be 1, and so you just keep the constant, and so r prime would be 1, and the derivative of the 2 and 3 would be 0. All right, now what do you do now that you have the partial derivative with respect to a? Well, we should really find the partial derivative with respect to b and c as well. Interestingly, they're all going to be 1s, right? So if r is a plus b plus c, then the partial derivative of r with respect to a is going to be 1. And the partial derivative of r with respect to b is also 1. The partial derivative of r with respect to c is also 1. All right. Now that we have that, we can plug into the formula. Okay, because the formula says sigma r equals the square root of partial with respect to a times sigma a, and then you got this. Now we know those partial derivatives. That's the point of doing that. So we can plug in. Alright, so we get 1 times sigma a, 1 times sigma b, and 1 times sigma c. Alright, if you recall, our sigma a was 0.05, sigma b was the same, and this one was the same too. In this case, it simplifies to this. The square root of the squares of all the uncertainties. It's an idea called quadrature. And it's like a Pythagorean theorem, but in this case it would be for 3 dimensions, you know. Alright, so we'll have this. Alright, so I'm getting that the uncertainty could be 0.087 centimeters. However, we typically want to round our uncertainties to just 1 sig fig. 2 at the most, but in many cases, just 1 is sufficient. Let's go back to what our final result was. Okay, it was 7.25. So I hope you can see that, like, actually the 0.15 is an overestimate of what the uncertainty is according to this more advanced technique, right? It works as like an upper bound of the error that's in the final calculation, but we can be like a little bit more precise about it. Instead of 0.15, I'll round it to 0.09, which is a little bit more rigorous.